about here is really just the kind of the high level points, a Mickey Mouse introduction or tourist guide. You really can spend entire career or entire careers studying optimization. So what I have over here is just a very, very limited view into that. But the goal, nevertheless, is to give you some sense of what it's all about, what you're trying to do. Okay, and hopefully at the end of next Thursday, or in about 2 weeks, you have some grasp of what does it take to optimize the system, what's really going on. Before we can optimize any system, the first thing we need to do is to model it. Okay, we need to kind of put it down in the form of a mathematical model. Okay, and what that means is that we need to take the system and kind of attach some parameters, something that we can use math on. And this is the part which actually is the hardest part. This is the part that there's no way to teach it other than to try it yourself a few different ways, because the same system can be modeled in very many different ways. Okay, just to take that simple example, I said there's a triangle. That's one way of modeling it. I can say, oh no, that's actually a bunch of chalk. I can look at the distribution of chalk, or I can look at some irregularities. I can focus on that. I can focus on visual perception, whatever. There are 100 different ways of doing it. So how you choose the model is the part that only comes from experience. So there is no actual way to do it. But what I'm going to do instead is I'm going to tell you what are the working parts of a model. Somebody says, here's a system, here's something, then you say, okay, I have to build a model for it. So what do you look for? Okay, so what you look for are basically 5 things. So the first thing is what I call the fixed parameters. A fixed parameter, as it states, is the constants. If you write a program, there's some constants, some things that you cannot change. It's given to you somehow, and you don't know how it came there, but that's the way it is. So those are the fixed parameters. So when you look at a system, kind of look at it and say, okay, what are the things that I know for sure are going to be true? What are the things that are given to me, not in my control? And those are called the fixed parameters. The second thing are what I call the control parameters. The control parameters are the knobs. These are the things you can change. Okay, so for example, you're driving a car. The fixed parameter is the size of the car, perhaps, or how much gas you can put in the tank. Okay, that's a fixed parameter. You can't really change that. Now, how much you press the accelerator or how you change the steering wheel, those are control parameters. You can actually do that. So you can turn the steering wheel, you can press the accelerator, you can press the brake. Those are the control parameters, and you have some control over that. The other thing we have what I call input parameters. Now, input parameters don't show up so much in optimization, but they show up in control theory. So I'm putting it in just for completeness sake. And input parameters are things that you cannot control, but they're not fixed either. Okay, they're so you're driving the car and you want to control it. You want to optimize how much petrol, how much gas you use, right? How far you press the accelerator. The input parameter could be the wind. Okay, the wind kind of changes direction, sometimes against you, sometimes it's behind you, and perhaps you're trying to do a cruise control system that maintains a steady pace, or let's say 70 kilometers an hour. And so the input is the uncontrolled extraneous input. Okay, it's uncontrolled. If it were controlled, I would do it over here. That could be the wind that's coming in. And then we have the output parameters. And what's the output parameters? These are the output of the system. This is the metric. For example, when I said you want to maintain your speed at 70 kilometers an hour, the output could be the absolute difference between the actual speed and the speed that you want to maintain. So let's say the speed you want to maintain is this, and the actual speed is something like that. Perhaps the area under this curve over here is the output parameter. Okay, that's one output parameter. You could also measure the amount of petrol that you use. That would be another output parameter. So these are quantitative ways of measuring the output of the system. Okay, and finally we have something called the transfer function. And the transfer function is, again, at some level the hardest part. okay, it tells you how the system translates from the control and the input and the fix to the output, okay. So it says, given all this, how do I get that? For example, again taking the car as an example, I have a certain velocity at this particular point in time. I have a particular fixed parameter, maybe the size of the gas line that connects the fuel tank to the engine, the capacity of the engine. All these are fixed parameters. The control parameter could just be how far down you press the accelerator, right? The input is the wind, so that's some kind of input. Wind is coming towards you or against you, something like that. The output could be your output velocity. Okay, so transfer function says how does the output velocity depend upon the size of the gas tank and the engine type, how far down you press the accelerator, and which way the wind is blowing. So just to kind of, here is the car. Let's say the wind is blowing in this direction, and I have some kind of engine over here, E, and I have the accelerator, in some position. Let's say this gap is X. Over there is how far above the base is X. So basically I'm saying the output velocity V is some function of the accelerator position, the wind velocity, okay, and the sort of the engine, okay. So this F over here, it maps from the accelerator position, the wind, and the engine size is the transfer function, okay. What does this function look like? Could be anything. All right, it could be anything at all. And one way of doing things would be you could measure it. You could take the car on the road and you could put the accelerator, 4 centimeters above the base, keep the wind constant, keep the engine constant, see what the output is, and kind of measure it out, and then you get one transfer function. Then you say, okay, I'm going to take a fan and blow it on the car, so control the wind velocity, keep it fixed, and so on. And I can then elicit, I can extract the transfer function F in this fashion empirically. Or the transfer function may be given to you because of some implicit, some inherent mathematical constraints. It may just be that we know this is a good modeling of the system, or but this is sort of something you don't really have any control over either. And that's a transfer function over here. So a lot of things depends on what the transfer function looks like. Okay, so what we're going to do now, and we're trying to get a little bit more into this, is that the control variables have essentially what I call feasibility constraint. Going back to the accelerator of the car, well, the pedal has to be no more, if this is the pedal, so this is the front of the car and that's the pedal. How does it even look like? Okay, I guess it looks something like that. And so let's call this to be X. We know that X has to be at least 0, right? It's greater than or equal to 0. And maybe the maximum value of this is some value max. So we can say 0 is less than or equal to X, less than or equal to max, right? And that max is sort of the full extension. When you're not pressing down on the gas at all, you have completely relaxed. That's how much you have. That's max. So this control variable lies in this range, 0 and max, okay? And 0 means you are going at full power, and max means you're going at 0 velocity, but that's okay. So this is the feasibility constraint that feeds into the transfer function over here. So already we're beginning to make progress in modeling the system, right? We can say, okay, we're going to find, we can say that X lies in this range over here. The next thing we want to do is we want to have essentially an objective function, okay? The objective function it's a function of the output variables. Okay. What are you trying to do? We're trying to model sort of the performance of the system. So what's the performance of the system? Maybe the performance of the system is this gap over here, okay? So let's just, maybe I'll draw this better over here. So let's say the first criterion I have, first output is this. I have time on this axis, I have the required velocity, and then I have the actual velocity like this, and I'll take the And let's say I'll just take some fixed time interval just to get time out of the picture. So let's say I define this time period as t, and then I take the total area under the curve, and let's call that area under the curve A over here, all right? And also I look at, in the same thing, I look at how much gas is being used, okay? So over time, the gas that's being used is going to be some monotone function, so let's say it looks like that. So I can look at this over here. Let's call that G as the gas that's being used. So I have two output variables, A and G, all right? So what I can define as the objective function, typically written as script O, is, let's say, is just A plus alpha G, all right? So I want to, basically, if A is large, my system is not doing too well. It's not really keeping the set point. I want the set point to be 70 kilometers an hour, and it's sometimes too fast and sometimes too slow. So A is a measure of badness. And similarly, G tells me how much gas I used. And it's also a measure of badness because I don't want that to happen either. So O is bad, O is high when you are away from the set point and when using too much gas, all right? So obviously we can now say that what we want to do is to minimize O, right? So our goal okay, subject to what? 0 is less than or equal to x, less than or equal to max. Okay, so let's just look at that for a minute. What's going on over here? What we did was to start right over here. You know, we have a physical system. We have a car, we have an engine, we have accelerator, wind, and all this other stuff, right? So somebody says, you know, optimize this for me, you know. Some car manufacturer presumably says that. And what we did was we kind of looked at it and we said, okay, what can we control? Okay, what are the fixed parameters? Well, the fixed parameters, we can define what the fixed parameters are. Perhaps the vehicle itself is a fixed parameter. What can we control? And we say, okay, the only thing you're allowed to do is to change the position of the accelerator. So we'll give that a variable, you know, x. So we already got started over there. And we said, okay, there's a feasibility constraint. I have something over here, right? The next thing we said was, okay, how can the thing change on us? Well, the input variables, wind is the only variable, perhaps other variables as well. Maybe you can use regular petrol, you can use, you know, a super high something or some other additive, I don't know. So those are also other input variables. But for the purpose of a particular problem instance, those input variables look just like fixed parameters. You really can't control them. You know, for one particular problem instance, you don't need to worry about that. Then we say, what are the outputs? Again, the person giving you the problem says, look, I really want you to make sure you obey the set point, you don't use too much gas. So immediately I get two more variables out of that, A and G, in a fairly normal fashion. And then I say, okay, I want to combine these two, and I put in a parameter alpha, tuning parameter. It tells me how much I prefer gas to being at the set point, okay? If I say, look, you can use as much gas as you want, I don't really care, we've just set alpha to 0, and then all you do is over here, but then we can play around with that little so tuning parameter that's alpha, and this allows us to define the objective function very, very, very straightforward fashion, and then we say, let's optimize it. Let's find this. This goal over here is optimization. This goal basically says, I'm now going to find some way of controlling x such that O is minimized, okay? And now we can start thinking about how do we do it, and so on and so forth. But at least now you're in the right frame of mind to appreciate what optimization is all about. Okay, it's about modeling and then finding the objective function and maximizing or minimizing O subject to the control parameters, and everything else is fixed. The fixed parameters, the input parameters are all fixed. And then, you know, of course, we have the transfer function that's also given to us. Yes. Sorry, what's your name?
My name is Hani.
Hani, okay.
And my question is regarding the transfer function. Is the definition that you're using other than the classical definition of transfer function systems? Because as far as I know, the classical definition for linear systems does not include the input. Is the relationship between input and output in terms of Laplace transforms.
Yeah.
And so it's y over the input,
Yes,
output
yes.
over the
Yes,
input,
yes.
and the function is only defined for
Yeah.
linear systems.
Yes.
And it does not include the input, as
Yeah.
you have mentioned here.
Does not include the control input, you mean?
Yeah.
Yeah, that's right. So I am using the transfer function loosely over here. It is, when you do control theory, we'll go into the actual notion of transfer quite precisely and in the transform domain, etc. Oh gosh. Okay. This is not something I expected. Okay, all right. Let me just kill this with maximum efficiency by removing the battery. Okay. This always seems to work somehow. So the transfer function is meant to be reminiscent of that. When we do optimization, we actually don't have a control input. Okay, we actually are not doing control per se, but I'm trying to use the same exact model for control theory and for optimization. That's why I'm putting this over here. In fact, what we'll end up very quickly seeing is that we only focus on f, which is some function of the inputs going to some objective function. I'll actually do that step in just a minute, but I just want to get the modeling out of the way. We use the same exact modeling for control theory as well, by the way. That's why I want to keep one single modeling for both of them. But so this is not exactly capital H that you would see, you know, in the classical control, but it's roughly in that same. It's in the same spirit. Yeah. Another question in the back, I thought. Okay. Anything else? All right. So what we're doing over here really is to start putting some mathematical bones into a practical system. That's the real takeaway message. Okay. So you go into some system. How do you start doing it? You know, I'm trying to give you the mindset you have to use to do the modeling, because this is the part which is actually quite tricky. Okay. What is the input? What are the control? Those are the things that become tricky. Okay. All right. I'm going to do one step further, as I mentioned to Hani, and then I will go back and do a second example just to, you know, give you a better idea of what's going on. So the step I want to go through which is further So let's say that O is some function G of some output parameters, right? That's what I said. O is some function G, and we said that the output is some function F of the input and control. Okay? So obviously what I can do is to just combine the two and just say O is some function H of the input and control. And actually I should probably say over here the fixed as well, just to be. Okay? Alright. Now these guys are constants. This is constant and this is constant from the perspective of a particular problem instance that we're trying to optimize. So we could just kind of lump them all into some constants, and we can just write this as basically H or some constants and control. Okay? It's nothing, I'm not doing anything, you know, particularly clever over here. It's just rewriting terms, and therefore we get the kind of classic optimization problem optimization can then be defined as choose the control parameters subject, right, to feasibility and we'll call optimize just a shorthand for minimize or maximize, right? To optimize Okay? That's it. In a nutshell. Your one sentence definition, so choose the control parameters, subjective feasibility to optimize an objective function O. Okay? And that sort of is the whole thing. Okay? So once you do the modeling, you got what you mean by control parameter, you kind of know what the feasibility constraints are, and then to optimize it with respect, optimize the objective function, we need to know the transfer function, and that's what we do, by modeling the system mathematically. If I change the inputs, how do the outputs change? Okay, that's the transfer function. Okay, any questions about this so far? Okay, let me do one more example just to kind of set these things in a bit more perspective, and this is the example that's in the book, and it's unlike the previous example which was I just made up. Yeah.
Excuse me, regarding the fixed parameters,
yes.
You mentioned we are never certain about the fixed parameters as well.
What do you mean we're never certain?
I mean we never know the exact, right, the triangle.
Yeah. Yes.
We are never sure about the fixed parameters.
Yes.
There are some variations.
Yes.
And we should consider robustness.
Yes.
Uncertainties.
Yes.
Do we consider such things here?
Not in this class, but once you enter into the mathematical world, so you have the real system, right? Then the modeling translates the model into the mathematical world. Once you're in the mathematical world, constants are constants and variables are variables. Okay, nothing changes roles. If you want to model if you want the mathematical model to include what you think of as constants as variables, that's okay. For example, just to give you an example of this, let's say that the engine has got a capacity of whatever 2.4 liters. That's you think is a constant. Now, one modeling is engine capacity 2.4 liters, and that's it, right? Another model is engine capacity is a Gaussian distributed random variable with a mean of 2.4 and a standard deviation of 0.1 cubic liters, for example. Right? Now I have this random variable, and we'll discuss that later, that actually says it's not a constant anymore, it's actually a random variable. I went from constant to a variable. That now says, okay, we cannot manufacture engines exactly. However, we can statistically sample them and come up with a distribution that fits this. Right? So then we have imported the randomness into the mathematical model. Right? That makes it more complex. Right, because now I can't just say divide by x, I can just do expected values, I can look at sort of, expected computations rather than actual computations. See what I mean? So it's a question of what do you import, how much complexity do you import into your model. The more complexity you import, the more realistic it is, but also it becomes more harder to solve. So we have to make this fine balance between complexity and realism, and that's why it makes it hard.
And when we import those probability concepts into our optimization, can we still solve it?
Yes, but it becomes much, much harder. For example, we can't do linear systems anymore.
Yeah.
Right?
But
so
non-linear programming.
Yes, but it depends. It depends. Stochastic optimization is something that people don't really understand very well. Okay. As I found out, I thought it was easy, but it's not. So for now, we'll just ignore it. We'll import only the basic stuff. Remember, you're not going to learn French here. If you want to know stochastic optimization, you do a C and/or grad class and then come here. Okay. Or come here and then go there. Okay. Right. Any other questions about this? Okay, let's do a simple numerical example and then we'll take a break. All right, so what do you want to do? I want to optimize a very, very, very simple system, and so I want to kind of tell you the system, and hopefully I'll ask you for questions about how it works. Here's what I have. I have a link. The link carries 100 packets a second. Okay, and if I send more than 100 packets a second, the excess gets dropped because there's no much capacity. All right, and what do I control? I can control how many packets per second I send into it. And what do I want to do? I want to make sure I don't drop too many packets and I carry as much as I possibly can. So this is a question that, presumably somebody could ask you, do it. So, well, let's try and model it. So I told you in words what it is. So what are the fixed parameters of the system? What is it that I know about the system? Anybody who's, yeah?
Bandwidth.
The bandwidth. Okay. So fixed parameter is basically it's 100 packets per second. So at least Earl read the book. Okay. But it's also obvious, this only number I gave you is 100 packets a second. It's fixed. You can't change it. It's given to you, whatever it is. Now, as you point out, maybe it's not 100. Maybe it's, it's kind of variable, and the on average is 100 packets a second. We'll ignore that. For now, it's 100, and that's what it is. What can we control? What's the control parameter? Anybody? Sorry? Number of packets sent. So my sending rate is what I can control. And I'll call that X, just for that. What's the input parameters? What are the uncontrollable kind of inputs into the system? Yeah.
The arrival process.
The arrival process. No, my arrival process is my sending rate. I can control that precisely. Remember, I have a link. I'm just telling you how many packets can I send. Okay. So.
No, they cannot be the same. Maybe the arrival process rate exceeds the.
You're thinking too far ahead. I have a very, very dumb problem. Asking you 1 + 1 = 2, and you're saying, in the complex plane, I can do this. Okay, no, we're just doing integers. Forget about arrival process. I have a link. Here, there's a link. I have some rate. I can send into it X, and this has a capacity of 100 packets per second. Whatever that means. Assuming fixed size packets, I guess. What's the input to the system? What are the input variables? The uncontrollable input, like the equivalent to the wind. Yes? There are none. That's right. The inputs is, we know everything. There's nothing extra in the system. It's just trivial. Okay, that's why I'm saying don't worry about the arrival process. There's no input variables that we don't know about. There's only one input, and that's us. Nobody else. Now, if you had cross traffic, right, who is trying to also simultaneously send stuff in, okay, now that would be an input, okay, because now you're sharing the link, but we're not even doing that. This is just too dumb. Yeah?
Packet loss on the link.
There's no packet loss on the link. If you had that, yes, that would be equivalent to sharing the link with loss process, which is coming in, right? It's exactly the same as a loss. You can model it that way. What's the transfer function? Oh, sorry, what is the output process? What are the output parameters? Okay, the two output parameters, I'll give you a hint. And you can't answer all because you read. Somebody who hasn't read the material, what are the outputs over here of the system? So let's go back over here. I have some sending rate, and if I send more than 100, it gets dropped. Okay, so what are the two output variables? Yes, Cameron.
Drop packets and
yeah, throughput. That's right. So throughput, what do you actually carry? And then the loss rate. Right? So, for example, if I send it 70 packets per second, my throughput is 70 and my loss rate is 0. If I send at 200 packets per second, my throughput is 100 and my loss rate is 100. Yeah?
But is loss rate an independent variable?
No, it's not. I never said it was.
Why do we then define an extra variable which doesn't have an extra meaning in it?
It has a meaning in it. If I send at 70 packets per second and the capacity is 100, the loss rate is 0. And if I send at 200 packets per second, what's the loss rate? 100. What's the throughput? Well, if I send at 500 packets per second, what's the loss rate? Okay, and the throughput is 100. These are two separate things. Why does it have no extra value?
But it can be inferred from the...
That's a transfer function. Right? Output is an output. Outputs are inferred from the inputs using the transfer function. Just because they can be inferred doesn't mean they are not output variables.
By increasing the number of outputs, we are making the system more complex.
That's fine. That's my prerogative. I can make it as complex as I want. In fact, it's a very simple system. But the point I want to raise is that the two outputs are in fact independent. You cannot predict the one output from the other. There's no correlation between the two output variables. There is a correlation between the input and the fixed parameters and the output, and that is the transfer function, which is what you expect. But there's no correlation among the output variables. Okay, that's important to know. So the output variables are in fact orthogonal in this case. It's not always the case. You can have correlated output variables. We're not studying that over here.
But for modeling a simple system,
yes,
it's better to have the less amount of...
You need both of these. You need both. You need both of these, actually. Just hold your question for a second because you'll see why you need both. Okay. Let's come to the transfer function. Okay. So what's the transfer function for throughput? Okay. Let's say throughput is... How do you define the throughput in terms of the sending rate and the fixed variable? What is it? Throughput equals Yeah. So it's basically nothing more than the min of x and 100, right? And the loss rate. So what's the loss rate in terms of the input variables and the fixed parameters? What is it? Sorry? Anybody want to? Yes, in the back. Aniket?
Yes, 0 or max or 0 minus 100.
Yeah. So the loss rate is the larger of 0 and 100 minus x minus 100. Okay, so if you send it less than 100, you get 0. If you send it more than 100, it's this, right? So now we are in a position to define the objective function. So right now the objective function is undefined. Okay, I just said, I don't want to lose too much, and I don't want to. I want to carry as much as possible. So now I'm going to make that more. I have to make that more precise. So one possible objective function is just O equals nothing more than throughput minus the loss rate. Okay, for example, so O increases as your throughput increases, O goes down as your loss rate increases. So this is a simple linear thing over here is all we need to do. And if you do this, then we just expand this out to be just the min of x 100 minus max of 0 x minus 100. So that's my objective function expressed in terms of x. And now you see why I need both variables, because I have to have the objective function that if you don't have loss rate as output variable, the objective function cannot have that as a value to be optimized. Right? I want to minimize the loss rate. And I'll just show you the graph. It's much easier to optimize it using just the graph. So on the x-axis is x, and on the y-axis is O. And we see quite naturally, takes a little bit of thought, not much, that at 0, we're going to have a throughput of 0 and a loss rate of 0. So my objective function is 0. At 100, I have a throughput of 100 and a loss rate of 0, so I kind of go up linearly. And at 200, I go down to 0 again. And after that, it kind of goes negative on me, because this is capped at 100. It's never going to be more than 100, and this can be, it can get basically larger and larger all the time. So the optimal point is clearly this one over here. I should send at 100. And intuitively, of course, this is just obvious. If I have a link which has 100, the best rate to send it is 100. There's no point sending any faster than that. So intuition and the math kind of match up, and you see this nice, straightforward picture over here. Okay. Any questions about this so far? Yeah.
So when you said there's no correlation between throughput and loss rate,
right?
What does that mean? Because in this example, it seems there is a correlation, right?
Not exactly. If I tell you the throughput is 50.
Loss rate is 0.
Oh, I see what you mean. Yeah. Given the fixed parameter and the throughput, yes, you can do that. Yeah. If you didn't know the fixed parameter, then you don't know. Yeah. Yes. In this case, yes. But it's because it's a really trivial system. But in general, you don't really know. Yeah. You're right. Okay. I should be more careful about that. Yeah. Any other questions about this? I managed to send 2 people to sleep. I won't tell you who your names are, so it's time for a break. And after the break, I'll kind of continue with the system of 2 variables. But basically, I've gone through the modeling, and definition, and then we'll start with the system of 2 variables in about a few minutes from now. Okay. All right. Okay. Can I erase this stuff, everybody? Okay. Okay.